All right, previously we have found areas underneath curves in the rectangular plane, but we haven't done that yet in the polar plane. So when you're dealing with the area underneath the curve in the rectangular plane, you would use rectangles or trapezoids. And we did things that could be measured horizontally and vertically. So the area of a rectangle, you could do length times width, or the x value times the y value, which was the function. And here, instead of having x and y, we have r and theta. So when we break down our polar region to find its area, we're not going to be talking about something that goes left and right and up and down. The area that we're going to be finding is going to be broken up into a radius and an angle measurement. So if you can see here, we've broken up this shape into a lot of different slices of pie, basically, where the radius might vary depending on the portion that you're looking at. But the theta is always the same, so that width or that degree measure that we're going, or radian measure, I guess, is the same for each one. And so again, we're still going to be using integrals because we use integrals to find the area underneath the curve, but this time we're kind of finding the area of a piece of pie rather than thinking about something that goes up and down or left and right. So we have to go back a little bit in math to think about how we get these areas, how you get a slice of pie, and we call those sectors. And a sector is a portion of a circle. So first we're going to look at the area of a circle. And if you guys recall, the area of a circle is pi r squared. So if we're finding the area of a sector, that's going to be just a portion of a circle. So the area of a sector would be a fraction of the area of a circle. So let's say that was a 60-degree angle. Then you would say, oh, 60 degrees, or whatever your theta happened to be, out of 360 multiplied by the entire area. So this is kind of like saying I'm taking this percentage of the entire area, and that would give me the area of my sector. In calculus, we typically don't do degrees, we typically use radians. So we're going to use this formula for area of a sector, but we're going to say that theta is out of 2 pi, so still using a full circle, we're just using a different measurement. And if you look here, we could simplify a bit. We can say that dividing by pi and multiplying by pi cancel out. So we have theta divided by 2 times r squared, or we could say that is 1/2 times theta times r squared. And when we're dealing with these problems, we're going to say that we know as the radius changes, the angle changes. We call that angle change d theta. And so when we go ahead and find the area of a sector, we're going to take the coefficient and we're going to put that out front of our integral. We know that we're using an integral because we're finding area. And the integral is going to be from alpha to beta instead of a to b, and that's because we use theta, we're using Greek letters as we use the polar unit. And then we're going to say that that is r squared times d theta. So we're seeing all the same variables that we could see up here, we're just writing it in a slightly different way. So that's the formula that we're going to be using. All right, on to the next page of notes. So here is where it gets fun because we know that the formula is pretty simple, but the pictures are not. So now we have to kind of apply what we've learned about that to kind of think through each individual problem to figure out how we could find the area of the entire picture, or in this case, we're looking at a rose and we only want to find the area of one of the petals. So when we look at this problem, I know that this is an odd coefficient here, so that means that I have 3 petals. If that had been an even number, then we know we would have doubled it to figure out the number of petals we have. And since we have an odd number of petals, I know that the interval it takes to complete the picture is just from 0 to pi. So if I want to find the area of just one petal, I can say the area of the entire graph, the area of all 3, would be from 0 to pi of r squared, so 3 cos 3 theta squared d theta. And then if I only want one of the petals, I'm just going to take this and I'm going to divide it by 3, or I'm going to multiply it by 1/3. All right, now what I've found is that a lot of students are having a really hard time kind of doing these problems by hand, doing this integration by hand. It's really easy at this point to just plug this in a calculator and see what the right answer is. But if you're taking the AP exam and you run into a problem like this and you're not allowed to use a calculator, you would be stuck. So we're going to go ahead and do this one by hand just to make sure that we still remember how to do it. I'm going to deliberately leave this space blank because there's another method for finding this exact same answer, and I'm going to show you both of those methods and then kind of let you choose which one you like. All right, so if we simplify this by hand, we have 1/6, 0 to pi, and now I need to square both of these things. So 3 squared and cos squared, so that gives me 9 cos squared of 3 theta. And then with that, I can go ahead and take that 9 and move that to the front. So that's going to give me 9/6. And now we've got cos squared 3 theta, and if you guys remember when we were using our different integration techniques, if we had a cos squared, there was nothing we could really do to integrate that with u substitution. We actually had to use the power reducing formulas to do that. So the power reducing for cos squared is to say 1 plus cos times 2 times the angle. So it was 2 times the angle, which would be 6 theta. Divided by 2. And I should have a d theta in there, I just don't really have room. All right. So 9/6, this is really 3/2. Okay. Now, I'm doing this completely by hand. I'm going to go ahead and pull out this divide by 2, so that 3/2 would have like a 1/2 in front of it. So that's going to give me 3/4. So again, that's because I had that 3/2 and I'm pulling out this 1/2. So then from 0 to pi of 1 d theta plus 3/4, 0 to pi cos 6 theta d theta. So this one is pretty easy to integrate. If you integrate 1, you just get theta. So that's 3/4 theta. The other one is going to be a little bit more work. It's going to be a u substitution problem. So u equals 6 theta, du is 6 d theta. Since we don't have a 6 hanging out here in the front, we're going to have to divide by 6. So that gives me 3/4 that I had already in the front. I also am going to have a 1/6 in the front. And then I'm integrating cos u du. So the integral of cos is sine. So I have 3/24 sine u. And now I can go ahead and replace that u with the 6 theta again. So 3/24, that's 1/8. So 1/8 sine of 6 theta. And I'll go ahead and drop that down. We still have that. So this is being evaluated from 0 to pi. And now I can go ahead and plug in my values for theta. So I've got 3/4 times pi plus 1/8 times sine of 6 times pi minus 3/4 times 0 plus 1/8 sine of 6 times 0. So 3/4 times 0 is 0. That's easy. If I can picture the unit circle, 6 pi is in the same spot as 2 pi. And the y-coordinate right there is 0. So that actually is 0 as well. Sine of 0 has a y-coordinate of 0. So that's 0 as well. So that means that the area of one petal is 3 pi/4. And if you want to go back to the beginning and just plug this in, you'll find that your decimal will match that. So again, we do not have to do this process every time. We just want to practice a few problems going through the entire problem by hand because we want to make sure that we can actually do it by hand if we need to, just in case it's on calculator inactive. All right. So now, an alternate way to do this problem. I promise every example does not take this long. I'm just showing you a lot of things all at once. So another way to do this problem by hand is to isolate one petal and to change your interval. So instead of finding the interval of the entire picture, you're just finding the interval of one petal. So what I'm going to go ahead and do is I'm going to I want to figure out where each petal starts and ends. And I know that the petals are coming together at the pole where r equals 0. So I'm going to go ahead and set r equal to 0 to see if I can figure out what radian measure starts and ends each of the petals. So I've got 0 equals 3 cos 3 theta. And then I'll go ahead and divide the 3 over. So 0 divided by 3 is still 0. And normally theta is between 0 and 2 pi when you solve for it. But we've got 3 theta. So we're going to be between 0 and 6 pi. I don't know if I'm going to find all those answers. So we're going to look, 3 theta is wherever we have x values of 0 on the unit circle. So that's going to be at pi halves, and 3 pi halves, and 5 pi halves, and 7 pi halves, and 9 pi halves, and 11 pi halves. I think that's all of the ones that we needed. Yep. And then I'm going to go ahead and divide by 3. So theta is pi 6. 3 pi 6, which is pi halves, 5 pi 6, 7 pi 6, 9 pi 6, which is 3 halves, and then 11 pi 6. So if you look at this picture, you can see here's my pi 6 right here. And there's my pi halves, and then here's my 5 pi 6 over here. And then here's my 7 pi 6, and my 3 pi halves, and my 11 pi 6. So to find each of these petals individually, you just have to use the angle measurements that kind of sandwich the petal. So if I wanted to find this petal right here, I could sandwich that petal. I would say that's 1/2 of pi halves to 5 pi 6, and then I'd have 3 cos 3 theta, and that would give me that one petal. If I wanted this petal right here, I would use 7 pi 6 to 3 pi halves, 3 cos 3 theta squared, 3 theta. Now this petal is kind of the tricky one, because if we always do smaller to bigger. If I do pi 6 to 11 pi 6, it's not going to find the area this way. It's actually going to do the area this way. It's going to go the other way, and I'm not going to get the petal that I want. So if I want to do this petal right here, I can do negative pi 6 to positive pi 6. That would be one option. Or I could do 11 pi 6 to 13 pi 6. But I have to have numbers that are next to each other for this to work. Otherwise, it's going to be going all the way around the circle, and I don't want to do that. That would be wrong. So to do this actual petal, the one that they really did highlight in the picture, I could go ahead and do it this way. And if you type those into your calculator, you're going to find that all 3 of those equal the same decimal, and that decimal is equivalent to this. So when you approach these problems, there's not one right way to do it. There's usually multiple approaches that you can take. All right, let's move on to example 2. That was a lot of work. It says find the area between the loops. So it doesn't want the whole shape. It wants just the area between the loops. So we have the outer loop and we have the inner loop. So first, for us to get an understanding of this problem, I want us to graph this in our calculator. So we've got 1 minus 2 sine theta. And on my window, I'm going to set my interval from 0 to 2 pi. Your theta step just basically says how like pixelated your graph is going to be. And the smaller the step, the more accurate the curve. So it's kind of like if you draw something on a computer and you can't actually draw a curve on a computer screen, you just draw with a series of straight lines, and the smaller your lines are, the better your curve is. So if you do like pi 12ths or pi 15ths or pi 20ths, that's good. An even better picture would be like pi over 300, but if you did that, it would take forever to watch it graph. So it's up to you. And then I think that x min and x max -5 and 5, I think that will be big enough for us to be able to see everything. So mine went real fast. I'm going to go ahead and make my step more precise so that I can make it graph slower. So if you see what's happening, it started right here. So it started on the outer loop, and then it graphed the inner loop, and then it finished the outer loop. And when we do these problems, for us to be able to find the area of a loop, we have to know what interval makes that loop from the start of the loop to the finish of the loop. Okay, so keep that in your head. We want to figure out what interval starts the loop and what interval is going to make that particular loop finish. So overall, we know that to draw one whole picture, it's going to take an interval from 0 to 2 pi. We know that's important. We can start the picture and finish the picture from 0 to 2 pi. For us to be able to figure out where the loops start and where they end, we have to see where the loops come together, which again in this case happens to be the pole. And so that's where r equals 0. So I'm going to go ahead and say 0 equals 1 minus 2 sine theta. And I'm going to solve for theta to see where these loops come together. So I'll minus the 1 over, and then I'll divide by -2. So I want to think, where on the unit circle is there a y coordinate of 1/2, positive 1/2? And you'll notice that that is at pi 6 and 5 pi 6. So what that means is that one of the loops, I don't know if it's the big one or the small one of the loops starts at pi 6. That's what that means. And then that loop finishes at 5 pi 6, and that's where the next loop starts. So what that means is I'm not going to use an interval from 0 to 2 pi. That shows me the whole picture, but it doesn't have me find one loop and finish one loop and then start the next loop and finish the next loop. So I know that my interval still needs to be 2 pi in length, but instead of starting at 0, I'm going to start at pi 6. So for me to figure out how big my interval is going to need to be, I'm going to say 1/6 plus 2. I still want it to be a distance of 2 pi. 13 pi 6. All right. So this, now I know this is going to start the picture and end the picture. I'm going to be able to draw the entire picture because this is a length of 2 pi. It just means that instead of starting over here on the picture and starting with the big loop and then drawing the little loop, finishing the little loop, and then finishing the big loop, instead of doing that, it's going to start somewhere else on the graph. So if I go ahead and I take my window and I change my interval from pi 6 to 13 pi 6, now when you watch it, you can see it is creating the little loop first, the inner loop first, and then it creates the outer loop. All right? And you can kind of tell which one is which because the inner loop is smaller and the outer loop is bigger, and this interval from pi 6 to 5 pi 6 is smaller than the interval from 5 pi 6 to 13 pi 6. So here's our inner loop, here's our outer loop. Now, if you think about the area of the outer loop, that's all of this stuff, right? That's the pink that I have, but it's also the inner loop. It's just the whole thing. So if we just want the pink area, then we're going to have to do the area of the outer loop minus the area of the inner loop. Okay, so now we know which interval we use to create our outer loop. We know which interval we use to create our inner loop. So I'm going to say the area of the shaded region that's pink, that on your paper is just gray. We're going to do the area of the outer, which is 5 pi 6 to 13 pi 6. Minus the area of the inner loop. All right. So that is 8.881, and I'm only going to type one of these in at a time because it means I don't have to type the same thing too many times. So I'm storing that so that I'm not using a rounded decimal before I should. And I'm going to go back in and change this to 5 pi 6 and change that to pi 6. 0.544. And the numbers we're getting are kind of supporting what we think, and that this number is the entire shape. And it makes sense that that would be a fairly large number and that this would be a much smaller number. So I'm going to store that as y, and then my answer is x minus y. So 8.338. All right, so we're going to try one like that again because I think that can feel kind of complicated the first time that you see it. So I don't know that this one printed very well for you guys, but that's what the shape looks like. Now, the nice thing about it is if you're dealing with a graph that's like the limacon without an inner loop, or the cardioid, which doesn't have an inner loop, if they ask for the area inside of that, you can just say the area from 0 to 2 pi, do the whole thing, you're good. You don't even have to worry about anything. You just have to worry about these limacons with the loops because they make trouble, basically. All right, so this one doesn't say find the area between the loops. It just wants the area of the inner loop. So we just have to figure out where the inner loop starts and where the outer loop starts. We just need to do that, kind of that little bit that was kind of complicated right here where we figured out what our theta was and we made sure that we knew which one was which. All right, so if we graph this on our calculator, 4 cos theta, you're going to notice the same thing happens again where you start off with like part of the inner loop, and then the outer loop happens, and then the outer loop gets finished, and then the inner loop gets finished. And for us to find the integral, for us to find the area of one loop specifically, we have to have that loop start and finish. We have to know what interval that loop starts on, what interval that loop starts and finishes on, I guess. So where it starts, where it ends. So to do that, we know that the loops come together at the pole. So we're going to say that r is going to equal 0. That's where the loops intersect each other. And so 0 equals 2 minus 4 cos theta. And I want to solve for theta. So I'm going to go ahead and subtract the 2 over. And then I'm going to divide the negative 4 over. So 1/2 equals cos theta. And then I'm thinking where on the unit circle, again, I know this is an interval from 0 to 2 pi. So where on the unit circle is the x-coordinate positive 1/2? And that happens at 5 pi thirds and at pi thirds. Right? Yeah, to the right 1/2, to the right 1/2. So pi thirds and 5 pi thirds. Sorry, look at my notes, make sure I'm doing this right. And then again, we know that the entire interval, if we start the picture and end the picture, it has to be a length of 2 pi for the entire shape to form. And so instead of starting at 0, we are starting at pi thirds. So I'm going to say 1/3 plus 2 because I want to be able to finish the shape. So that's 7 pi thirds. So I have to think about which interval is bigger, which interval is smaller. From pi to 5 pi is going to be bigger than from 5 pi to 7 pi. So this is the outer loop, this is the inner loop. And if we change that on our calculator, oh gosh, that was silly to watch. Pi thirds to 5 pi thirds, we're going to be able to watch that outer loop form. There we go. If I want to watch that inner loop form, then I can say 5 pi thirds to 7 pi thirds. There's our inner loop forming. All right, so if I only want the inner loop, then I should just be doing the integral on this interval. So 5 pi thirds to 7 pi thirds of r squared and if you plug that into your calculator, you're going to get 2.174. All right. For the next problem, we want to practice finding the points of intersection between two different polar graphs. So one is a limacon with a loop, one is just a circle that's centered at 0 with a radius of 1. So for us to find points of intersection of anything, we always set them equal to each other. So 1 equals 1 minus 2 cos theta. And then we're going to go ahead and solve for theta because our points of intersection are going to be written as r theta, right? Normally we'd have x and y, but here we're going to have r and theta. So I'm going to minus the 1 to the other side, and I get 0 equals negative 2 cos theta. And I didn't write it over here, but again, as it is true with most of the problems, our intervals from 0 to 2 pi. Okay, so for me to finish this, I'm going to go ahead and divide the negative 2 over. And I'm thinking about where on the unit circle do I have an x value of 0. That happens twice. That happens at pi halves and at 3 pi halves. And so we want our final answers to look like points. And so you won't always have it where you just know that the r coordinate is 1 because that was one of your equations. So if you want to figure out what your r value is, you can just take that theta and plug it back into an equation. So typically, you won't always have an equation this simple. You might have two that are like this, and it doesn't matter which one you plug it back into, you just plug it back into one of them. So I'm going to go ahead, even though we already know the answer is 1, just for the sake of you having this on your notes, I'm going to go ahead and actually show us doing this by hand. So 1 minus 2 cos pi halves and 1 r equals 1 minus 2 cos 3 pi halves. So this is 1 minus, we said cos of pi halves was 0, right? Yeah. 1 minus 2 times 0 equals 1. 1 minus 2 times 0 equals 1. And so that means that our 2 points of intersection are 1 pi halves and 1 3 pi halves. So you can see those two intersection points. One's right here, one's right here. Now you'll notice that when we did that problem, I'm all like, yeah, hey, we're done. And some of you might be looking at that like, ooh, isn't that an intersection point right there? And the answer is no, because intersection points happen when the graphs cross each other. The graphs are not crossing each other here, they're coming up alongside each other right here. And you can really tell when you try to think about what that theta value is and what would happen if you plugged it in, So the theta value right here is pi. And if you try to plug pi in, knowing that it should fit into this equation, you'd say 1 equals 1 minus 2 cos of pi, if we're looking at that point. It's 1 equals 1 minus 2 times cos of pi is negative 1. 1 equals 1 plus 2, which is not true. So that is actually not a point of intersection. The point appears to be an intersection. The graphs come up alongside each other, but it is not a point that makes both equations true. So our only points of intersection are where the graphs actually cross each other.